All right, here we go. So the last 5 lectures, we've been talking a little bit about introduction of colloids, and we talked, well, quite in depth about how to make one class of them via emulsion and via mini-emulsion polymerization. And now we're going to take a little shift in gear, really, and we're going to talk about some physics. So the topics for the next 2 to 3 lectures will be how does stuff move. That's it, really. So we're gonna go a little bit through history, and then hopefully we'll end up some really cutting-edge science at the end of it. And you can be quite creative in that as well. That's the plan, at least. So you can come up with some good ideas on how we can make the ultimate nanobot in a way, or whether this is possible or whether this is not possible. So hopefully by the end of the lectures, you should get a little bit of an idea on whether those stories you see in the popular press about little robots swimming in your body and fixing things, whether that would be possible or whether that would not be possible. Okay, so this is the kind of plan. So we want to look at forces and interactions on the colloidal scale, and we begin with forces that have to do with movement. And obviously, if things can move, they can move up and down and to the left and to the right. And so there's some questions that you can ask yourself. And one of the interesting things to look at, for example, is Michael Faraday's gold soul, which he prepared in 1857 and which is in the Royal Institution. And this is what these things look like. So you can see there's a bunch of jars. And in that jar, there's a little bit of a colored soul, and the color comes because of the quantum confinement of the gold particles. At least that's what they claim. You could be cynical. You could say, maybe it's not gold, maybe it's just a bottle of Ribena. Yeah, and they fool us. So the idea is now to figure out who is right about this, or maybe they've remade it. So when you think about it, from a very simplistic point of view, the bulk density of gold is 19.3. Density of water is 1. So you would imagine that if I would have a gold bar and I would chuck it into water, it would immediately settle quite rapidly. Now, because of the color of this gold, we're dealing with kind of gold particles on the nanoscale. Now the question is, why don't they fall down? They've had quite a long period to fall down, over 150 years, and they still seem to be quite happy in that jar, maybe or maybe not. So that's one question that you could think about, like, why is this, or are we fooled? Now the other question related to that is like a mini emulsion. So we have a mini emulsion, we talked about the last lecture, of droplets that are like sub-micron in size, and the density of styrene, for example, is 0.909, so it's lighter than water, and you can make a mini emulsion, and then you can leave it for about, well, if you put a hydrophobe in there, you can, if you do it right, you can leave it for a few months, and it remains stable. So it means that the styrene doesn't float on top, whereas it's lighter. So if gravity is right, it should cream, it should go up. So these questions, or these observations, they're quite interesting. And obviously, physicists have looked at this for, I would say, centuries. And they wondered what the underlying forces were, and hopefully we're going to unravel this in the next hour. So here's the first thing that was dealt with by a few people. So Archimedes, 287 before Christ, he already observed a force that was related to buoyancy. So it basically meant that if you would replace a volume in a liquid, you could float things. And then Newton basically composed the laws of gravity. So if you think of a particle either in air or a particle dispersed in a fluid basically, and the fluid can flow, then you could say, okay, if we're looking at vertical movement, then gravity will pull the particle down, and the buoyancy force, well, if the particle is in air, the buoyancy force will work opposite and will drag the particle up. Yeah? So, is this all that there is to it? So, do people agree or disagree that this is the complete picture? So, if you think, well, okay, this should be right, then press A. And if you think, no, there's more to it, then press B. Okay, the overwhelming majority says there's more to it. Maybe only because we're at slide 2 or 3 in the presentation, so you might think. So, but yeah, that's the answer is correct. So what other force is important then? Anybody got an idea? What have I forgotten here? Interaction with surfaces. Could be, yeah, could be right. Surface is right. So, anything else? Anybody another view on this? Brownian motion. It's a nice term. So we'll come back to Brownian motion. Anything else? Why can an aeroplane fly? Why doesn't it just fall down from the sky? Different pressures. So, okay, any word that's related to pressures? What's important for a Formula 1 car and important for an airplane and important for Olympic swimmers? Aerodynamics, which is related to drag. Yeah. So drag is important. And so we have to add an extra force to this. And actually Newton already realized this, that there was more to it than just this simplistic or oversimplified view of gravity goes down and buoyancy in this particular case, when an apple falls from a tree, it goes up. The creationists would say that only fertile apples fall down. Everybody else just, follows the rules of physics. So, so here, this is a term what we have to be aware with, and that's a property of materials that can flow and resistance to flow in a way. And those things are expressed, or the measure for that is called viscosity, which you may or may not have heard of. If you've done polymer chemistry, you probably have heard of viscosity. Maybe in a lab experiment you've done something related to that. But for those who have forgotten it or have no idea of what it was, here's the concept of it. So here's a picture on the left, and it shows 2 parallel plates with a fluid in between. And what I'm going to do is that I'm going to move the bottom plate with a specific velocity in one direction. And I'm going to see what's happening, how the fluid is going to respond to this. Yeah? So at time 0, I'm going to set my lower plate in motion, and then you can see that the velocity profile slowly but surely builds up. And the end result is that the first layer of fluid that touches the bottom plate will have a comparable velocity to the bottom plate, and then obviously the fluid that touches the top plate doesn't flow at all. Now if I do this with a relatively okay speed, so not insanely fast, yeah, then what I'll get is that I build up a lamellar flow profile, which basically means that you can imagine it's like a deck of cards. Imagine the fluid is a deck of cards, yeah? And obviously in between the cards there's a certain resistance. So if I move the bottom card, the card that's lying on top of it gets dragged along a little bit. Yeah, so if the top card is fixed and the bottom card moves, you can see that you slowly but surely drag along everything, and then you get a gradient of velocities over this, profile of deck of cards. The same thing happens with this fluid. So what Newton realized that for these kind of fluids, that if I apply a force, that's basically related to the velocity, which is v, which is the constant velocity of the bottom plate, divided by, in this particular case, the thickness of the fluid layer, times the area between these plates, multiplied by a term that deals with the response of the fluid, and that term is called viscosity. The symbol for that in this particular case is mu. Sometimes you see the different symbol eta for that. So they're used, if you read physics papers, you get the mu. If you read chemistry or IUPAC papers, you get the other symbol. So now, not all fluids are Newtonian. So fluids can behave completely different, and therefore viscosity as such not necessarily is a constant. Viscosity can be a function of shear rate. So if I deform the liquid more or at a higher speed, I can get a behavior that's nonlinear. You get a nonlinear response in viscosity. That goes a little bit too far for this, because we're going to go down to very, very, very small scale, which means that deformation forces are relatively small. Yeah? So you just have to remember what viscosity stands for. Okay. So here's the interesting thing. So let's add another force. Some people said already in the audience there is drag force. So if my particle moves down, as in the picture here, then I've got gravity going down. So it's a particle falling from the sky, for example. I've got gravity going down. I've got buoyancy force going up, counteracting, because that's the volume that's replaced. That volume of air is replaced by the sphere in this case. And I have a certain drag force. Now, the law of this drag force is described to, in a way, two people. If you read Newton's book, then it comes in there, not very explicit, but it's in there. So it's actually ascribed to Rayleigh, Lord Rayleigh. And what they did in a way was looking at how cannonballs behaved if you would shoot them, and how fast they would move. And as a result of that, they came that there would be a certain law that had to deal with drag. So what they come up with is that the drag force counteracts gravity. So in this case, I've got there a minus sign. Is half times the density of the continuous medium, the density of the fluid, which in this case is air, times A. And A is the cross-sectional area. So it's not the area of the sphere in this case. With cross-sectional area, I mean, just in this particular case, the area of the 2D projection in the direction I move. So if I look from the bottom, I don't see a sphere, I see a circle coming at me. Yeah? So that's the area I need. So that's, pi r squared in this case. V stands for velocity to the power 2. And CD is the drag coefficient. And a drag coefficient is a function of, what does my object look like? The shape of my object is really important. And it's also a function of how fast it moves. Now, if I'm moving through a liquid, so movement by itself, so, the laws of Newton, those are inertial forces. So velocity, gravity, those type of forces are inertial forces. So, whereas the other forces that we talked about is the viscous forces, is how the liquid responds. So if you would take the ratio of those two, that would give you a nice information. So if inertia is dominant, if I would take the ratio of inertial forces over viscous forces, if if I move really fast, that means inertia is dominant of that ratio. If I move really slow, then the viscous forces would be dominant. Now, the ratio of those two is expressed as a dimensionless number, which is called the Reynolds number. So in fluid dynamics and in chemical engineering, that's a really important number because it tells you which forces dominate. Is viscosity the most important, or is inertia the most important, or are they slightly competitive with each other? So, and the Reynolds number in this particular case is the velocity times the density times the characteristic length divided by viscosity. So a characteristic length, for example, could be the diameter of the sphere in this particular case. Yeah? So the other thing then, so what is CD, which is the drag coefficient? Now, what are typical numbers for this? A bullet has got a CD of about 0.29. A sphere is about a half if it goes extremely fast. So, you know, if a hailstone falls from the sky. Obviously, that number is different. So the drag force for a sphere that goes very slowly through a liquid is 24 divided by the Reynolds number. And we come back to that, why that is. A ski jumper is about 1.1, and a Boeing 747 has a very low drag coefficient. It's about 0.031. So when you know these things, you can put it into this equation, and you can make this work. So you can actually calculate how fast objects move. Now, because you have three forces in this case that balance each other, so one force goes down, two forces go up. If you do a force balance, you'll reach zero at a certain stage, which means you reach a terminal velocity. Yeah? So if you fall from the sky, you don't go faster, 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 faster. Yeah? Drag starts to become important, and drag in this particular case is related to velocity to the power 2. So the drag force becomes larger and larger and larger until it balances out. So if your force balance is zero, you reach your terminal velocity. And that's the velocity, your maximum velocity, in which you would fall down. So you can work that out. You can work that out if you know your cross-sectional area, if you know your mass, obviously, and if you know your drag coefficient. So comparable, for example, you know, a ski jumper. You could imagine if you would fall down horizontally, then your drag coefficient would be similar to the ski jumper. So you would fall down slower than if you would just fall down vertically, obviously. So here are some terminal velocities, which I just took from the Hyperphysics website. This website made an assumption. They ignored the buoyancy force. Buoyancy, obviously, in air is very low because the density of air is very low. But if you want to take that into account, you need to do that, and then these numbers are modified slightly. But here you see typically how fast you will fall down. So if you're a skydiver and you fail to open your parachute, you go down with about 60 meters per second. It's quite fast. So a golf ball, 2.1 centimeters, goes down 32 meters per second. A raindrop of 0.2 centimeters, so quite a small drop, still falls down pretty hard, 9 meters per second. So you can calculate what the impact is, right? So if there would be kinetic energy, half mv squared, if it hits the bottom, you kind of know what the energy is that needs to be dissipated. So it's quite interesting. Obviously, these things are objects that fall from the sky. Now, if you're in a liquid, then your buoyancy force becomes way larger, yeah? Because the density of the liquid, and therefore the cohesive energy of the molecules of the liquid, basically increase not only the buoyancy force, but also the drag gets influenced as a result of that. So how does that work? Now, okay, so there was another person that did experiments related to that, and that was Gabriel Stokes. Yeah? So Stokes basically stated that the drag force was related to a drag coefficient, which he called B, times the velocity. So he didn't have velocity to the power 2, he had velocity to the power 1. Yeah? And by solving the Navier-Stokes equations, which is extremely, well, rather challenging maths, and by doing experiments, he found out that the total drag force on a sphere was equal to 6 times pi times the viscosity of the liquid times the radius of the sphere. Now, if you would take the other drag equation with velocity to the power 2, and if you put in that your drag coefficient is 24 divided by the Reynolds number, you should get the same expression. So I want you to have a go at that and see whether that's true or not.